Babies, how we doing today? We're going to start our new unit here on momentum and impulse and looking at the conservation of momentum. So this lesson we're going to focus on the idea of momentum and impulse and what's called the momentum impulse change theorem. All this has to deal with is kind of related to Newton's laws, and actually the idea of momentum is something that was derived from Galileo and Isaac Newton. You might know the word momentum as like from sports, whatever it is, but when something's going right for somebody, they got momentum going. So momentum is just a measurement of the amount of oomph something has. So if I have like a ball rolling or a car moving down the street, we say that that object has momentum. Momentum is just simply a measurement of the amount of motion, plus it also takes into account the mass. So momentum, we kind of can formulate just a simple equation. Call this P. P represents momentum. The reason why we use P is just some stuff that Isaac Newton came up with related to calculus. Obviously, it relates two things, the mass and the speed. So the mass is how big an object is, and the speed is how fast it's moving. So momentum is going to have to deal with two things, the mass of an object and the speed of an object. So here we're going to symbolize momentum with that symbol P. Unit-wise, there is no fancy unit for momentum. We have mass, which is measured in kilograms. We have speed, which is measured in meters per second. So momentum is just simply a measurement of how much kilograms, or how many kilograms, and how much speed in meters per second. So we symbolize it as kg/ms, so kilogram meters per second. Again, so key thing here is that we did a unit on vectors. So momentum is going to be a vector quantity. However, we are going to simplify things and only look at vector quantities in terms of one-dimensional momentum. So we're not going to do anything two-dimensionally. But again, just the idea of vector. Momentum is a measurement of an amount, again, of motion an object has, so that mass and speed. However, momentum is dependent upon the direction. You can see here I have just a collision going on between an object that's moving to the right versus an object stationary, and how that would be different if I would have two objects moving here. So obviously, if this object's moving, it has momentum. This one does not. But when they collide, obviously something's going to happen. And here we have momentum, but this object's moving to the right and this object's moving to the left. And what would happen in this collision is obviously something different, but the collision itself is going to be dependent upon the direction in which these two things are moving. So momentum is going to be a vector quantity. It does depend on direction, kind of like forces and motion that we talked about in earlier chapters. So let's go through just a couple simple examples of calculating and understanding momentum. So let's say that I have different objects. Again, momentum is going to be related to the mass of an object and the speed. So to find the momentum, all we got to do is take the mass of that object, whatever that object is, times the speed of that object, and that's going to give me its overall momentum. So if I take 60 kilograms times 9 meters per second, that's going to give me momentum of 540, and then units is kilogram meters per second. Continuing on, if I had a car, let's say 1,000 kilograms, at 20 meters per second, that would give me 20,000 kilogram meters per second. So in this case, you have a larger car moving at a larger speed, so notice its momentum is much bigger. Then we have a 40 kilogram freshman moving at 8 meters per second. That would give me 80 kilogram meters per second. So comparing this again, it depends on two things, the mass and the speed. So now understanding the two variables, mass and speed, okay, what we can do is think about what would happen to the momentum if we change these things. So understand momentum is going to be dependent on these two things. So let's say that I have a car that possesses 20,000 units of momentum. What would be the new momentum if I were to make these changes? So if I were to double the velocity, so whatever the velocity is, if I were to make it double. So the relationship here is this. If I were to make this velocity much bigger, because I am multiplying these two together, there's actually a direct relationship between the momentum and the mass, as well as a direct relationship between the momentum and the speed. So if I change the speed, it's going to do the same effect on the velocity. On the momentum. So if I double the velocity, what I'm going to get here is 40,000 units of momentum. Okay. If I were to triple the velocity, again, that momentum is going to do the same effect. It's going to triple as well, so it would go to 60,000 units of momentum. Same thing is true as that if I were to double its mass, so if I were to change the mass, if you make something bigger, it's going to have more oomph to it, it's going to have more momentum, it's going to be harder to stop. So doubling the mass is also going to have a direct impact. So if I double the mass here, it'll give me an overall momentum of 40,000 units. And then if I were to change both, so if I were to double velocity and double mass, it's kind of like a double-double, so that would be a quadruple, so my momentum would be 4 times bigger. So this would actually give me 80,000 units of momentum. So mass and speed obviously are going to dictate the momentum. And again, think of momentum as having that oomph to it. All right, so the more mass, it's going to be harder to stop, more oomph. And also speed, it's got to be moving to have momentum. Okay, so again, momentum is going to be related to the mass and the speed of the object. So here I have an example where we have 3 different individuals, a halfback, a tight end, and a lineman. It's from the game of football. So understanding these 3, lineman normally is the big dude. You can see the mass here of 120. Tight end's kind of that medium person, 90 kilogram mass, and the halfbacks usually are smaller individuals, so 60 kilograms. So obviously it's something that has more mass. Normally, as we've talked about with forces and things, we'll normally move a little bit slower. So let's say here I have this ticker tape, again, with these dot diagrams that's going to show how these objects are moving. Spacing between the dots for all 3 you'll see is the same, consistent, so that means they're all moving at a constant speed. But you notice that the spacing for each individual person is a little bit different. So based on the spacing, the lineman's speed is told to be 3. So based on this, if we have a tight end, again, that comparing the mass, we know the lineman's 120, the tight end's 90. That if this person is smaller mass, probably going to move a little bit faster. So based on the dots here, I'll just kind of pick here. If I look at that spot, I got about 6 dots to every 3, so we can say it's twice as fast. So I would say that the tight end's moving 6 meters per second. Kind of use the same relationship for the halfback who has a mass of 60 kilograms. I'll pick, again, I'll just look at here at this spot. We have 9 dots for the lineman, 4 dots for the tight end. We only have 3 dots for the halfback. So we said it was about times 2 here. So compared to the halfback, we're looking at about 3 times as fast. So that would be about 9 meters per second. So again, looking at the individual's mass and speed, obviously we talk about more massive something is, usually it's harder to move, so speed-wise, normally they'll go at a slower speed. But when we can't compare the object's momentum is going to look at the object's mass and the speed combined. So not only how big something is, but how fast they're moving. So if I want to find the momentum of each of these individuals, what I'm going to do is just simply take their mass times their speed, and that'll give me an indication about their momentums. What I'll get for the momentum of each of them, I'll get 360 for the lineman, 540 for both the tight end and the halfback. So the greatest momentum would be shared between the tight end and the halfback. So as a concept, momentum is a very simple idea. It's just a relationship between the mass and speed of an object. But the momentum of something can change. As we talked about in our second chapter with forces, is that when you apply forces to objects, that's going to cause an object to change its motion, especially if the forces are unbalanced. So in terms of momentum, anytime an object's momentum is changing due to a force, we're going to call that an impulse. So an object is going to experience what's called an impulse if its momentum ever changes. And the impulse is simply equal to the amount of force that's being applied to an object. But in terms of momentum, since the object's speed is going to change, those things don't happen instantaneously. So forces are also a time-based quantity, that when I apply a force to something, that if it's going to gain speed or lose speed, that's going to take a certain amount of time. So that relationship between force and time, which changes an object's momentum, is going to be called impulse. So this is actually something we didn't really focus on when we did Newton's laws, is we didn't think of the forces as being a time-based quantity, but they technically are, that when you apply force, there's going to take some time for that to happen. So like, for example, if we have a football player that's running down the field, in order to stop this player from moving, in order to change its momentum, we would need to apply a force. However, let's say in this guy, this force is being applied back on this object, it's going to take some time before that person's momentum actually comes to a complete stop, or whatever it might be. So it is a time-based quantity. So impulse, we symbolize obviously I for impulse. We have the 2 variables, force and time. You'll notice here that I have delta t. So delta, that triangle, again, delta t is just going to represent that we're looking at a time interval instead of at a specific time. So for example, if I give you a time interval here of 5 seconds, that means that the length of time for that momentum to change was 5 seconds versus if I give you, let's say, 0.5 seconds. Again, it's not for at that specific time, but it's looking at a duration of a half a second. Okay, so impulse again is going to be that change in an object's momentum. So here I have again one of these little dot diagrams that shows an object's motion. So impulse occurs when an object's momentum changes. So if we look at this diagram, approximately when would the object experience that impulse? So an impulse again is going to be a change in momentum, and change in momentum specifically is going to change. So if we think of momentum, it's going to change the mass or the speed. So again, impulse is going to be that force in time that's going to change the object's momentum. But which of these two variables is easier to change, mass or speed? In this case, it's going to be the object's speed that is going to be easier to control. To change an object's mass, I would have to do something drastic, okay? So when you apply an impulse, normally what you'll see is that an object's speed is going to change. So on this diagram, you'll notice here that I have a constant speed going on, but eventually, say about here to here, I'll just kind of circle both these dots, you'll notice that the spacing between the dots is going to start to get smaller. So right at this location is when the object would experience an impulse because its motion is going to change. And what we know is that if its motion is changing, that this object would be experiencing a force, which in turn would create an acceleration back against that object, which is going to cause it to slow down. So an impulse, again, is looking at when the object's momentum is changing. All right, so taking that idea now, let's say that I have two objects here that are colliding with a wall, and I want to know which one experiences a greater impulse. But notice here what I have, this is going back to the idea of momentum being a vector, is that I have an object changing direction. So you'll see in case A and case B that the object is going to begin with the same speed just based off the spacing, going to collide with a wall and is going to bounce back as if they took an L last night. It's going to bounce back in the opposite direction, and we can look at the dots and compare their speed. So I want to know which case would one experience a greater impulse or an overall change in momentum. So what you got to do is you got to look at the speed. So in this case here, the speed in the beginning is the same. In this case, the speed is going to be a little bit slower than that. So when we have an impulse, that impulse is going to create a change in the overall speed. So I'm going to put this delta V here to represent the change in speed. So let's just fit the numbers to it. Let's say here that in case A and B, they're both going at 20 meters per second before they hit the wall. You'll see that in case A, as it bounces back, by the spacing of the dots, I can see that it's going to be half as fast. So I'll say here on the bounce back, it's going to be about 10. And for case B, just based on the spacing, let's say it's about 15. But notice that they're going in opposite directions. So when I look at the change in speed, we're starting off as a rightward positive 20 meters per second. But then in the bounce back, we have negative speeds because the direction changes. So when I look at the change in speed, think of this as the final speed minus the initial speed. So if I want to find the overall change in speed, here would be the final negative 10 minus positive 20. So an overall change in speed is going to be negative 30 meters per second for that change in speed. What that negative 30 means is that it lost the original 20 and then gained back 10, so that's an overall change of 30. Versus in case B, ended with negative 15 meters per second and again started with that 20, so if I were to subtract those, I would get negative 35 meters per second as an overall change. Okay? So in this case, the overall greater change in impulse or change in momentum would be case B because on the bounce back, it gains more speed. So impulse is going to be that overall change in speed, but we got to look at the speed that's taken away, and if it bounces back, how much speed it's also given. All right, I want you guys to try this example on your own. What I'd like for you to do is to think about which of these objects would experience the greater change in momentum or impulse. So again, impulse is going to be related to that change in speed. So in case A and case B, try and figure out which of these two would have a greater impulse. All right, so you would get negative 15 meters per second. So again, losing 10 and then gaining 5, so that's an overall change of 15. Here we're losing 30 and then gaining 28, so that's an overall change of 58. So the greater impulse here would be found in case B with the overall greater change in speed. Okay, similar question in 5 now, but in 5 we're looking at a graph of velocity versus time. So first of all, in this graph, where is the impulse shown? So the impulse is going to be found here where we see that the velocity is changing. So in case A and case B, both of those, that's where the impulse would be found, okay? So if we want to find the overall change in speed or the impulse, again, we have this starting off at 5 meters per second, and this is noticed in the positive portion of the graph, and then down here we have negative 3 meters per second. So if I wanted to find the change in speed, it would be that negative 3, which it ends with, minus the start, which is positive 5. So I would have an overall change in speed of negative 8 meters per second. It loses the entire 5, and then it gains an additional 3. And you'll notice that that change in 8 would be the whole height of this line. So if I were to go down from here to here, that would be a change in 8. And again, we talked about how that impulse is a time-based quantity, so you'll see that this does move forward a little bit, but that is that delta t that we looked at before. All right, so why don't you guys try case B? What would be the impulse or the change in speed there? So in B, you would get negative 4 meters per second as the overall change in speed based on that impulse. Okay, so again, impulse is going to be that change in speed that we see, and obviously because the object's momentum depends on both the mass and the speed. Okay, so now to connect these things again, momentum is an object's mass and speed, and we have impulse, which is that force and time that causes an object's momentum to change. So this is called the impulse momentum change theorem, and all it is simply an application of Newton's second law. If you remember Newton's second law, that said that the acceleration an object experiences is equal to the net force divided by the mass, okay? Now, the acceleration, again, is how much speed an object is gaining or losing. So the acceleration is going to be an object's change in speed over a certain amount of time, and that, again, is going to be caused by that relationship between the force and the mass. So this, again, is just rewriting acceleration based on its definition. So what I'm going to do is I'm just going to do some simple stuff you might have learned a long time ago and cross multiply. I'm going to take mass and speed and multiply them together, and force and time. And what I get is this relationship. I get the force times the time. And again, this would be the net force, but I'll just simplify it as F. So that's F times delta T, force and time, is going to equal the mass times the change in speed. So looking at this is what's called the impulse and momentum change theorem. F times delta t, this is called the impulse. This is how the momentum changes. And then obviously this side is going to be the momentum change based on m and delta v. So how to read this equation is you have a force acting over a certain amount of time that's going to cause an object to change its speed. This right here on the left side, the way I like to think about this is the cause. This is what's going to happen. And this is the effect. This is how much momentum the object is going to gain or lose based off of that. To show you this relationship, we're going to look at example 6 in this table. Okay, so here you're just given some values, and we're going to use that relationship of the impulse and momentum change theorem to try and fill out the table. So for example, in this table, if I know that like the mass is 10 and the velocity is negative 4, I automatically know that its momentum is going to be negative 40, and this will be its momentum change, okay? So its momentum change is obviously caused by an impulse. So the idea is that whatever my impulse is, it's going to be same as the momentum change. It's like the cause and the effect. So if this is negative 40, then that means the impulse is negative 40. Now, impulse is caused by a force and a time. So if the time of that momentum change was 0.01 seconds, what force would cause that impulse? So to do that, what I would take is just use the equation for impulse. I'll write it above. I equals F delta T. So if I know the impulse is negative 40, I know the time is 0.01. I'm just simply going to divide, and I would get a force that's equal to 4,000 newtons. So 4,000 newtons would be that force, okay? So kind of follow that same relationship, and I'll do one more row, and I'll have you guys fill out the table. But again, impulse and change momentum are going to be the same. So again, if I see negative 40 as my impulse, I know then that my momentum change is also going to be 40. So if the mass is 10 kilograms, again, it's going to experience an overall change in speed or a change in velocity of negative 4. But again, that's going to be dependent upon, this is the result, this is what happens, the effect, okay, but that's going to be caused by a force acting over a certain amount of time. So these two variables must also multiply to the same number. So now notice here my time was 0.01, so 1/100th of a second. Now we're 1/10 of a second. Okay, so this is a little bit quicker, this is a little bit slower. So let's see what happens to the force. So if I take that same 40 units of impulse and I divide it by that time of 0.1, my force now in this case is going to be 400 newtons. This brings up a little point then that, again, the mass and the speed must multiply to the same number as the force and the time. So if the mass is the same, it's going to experience that same change in speed. But here we see another relationship formulating with time and force. That time and force have this relationship that if the momentum change is going to be the same, here both -40, that if the time is longer, so longer duration of time, and this is not that great of a change, but a longer duration of time, we're going to see that the force is going to decrease, okay? So here just real quick, if I see an increase, in the time, I'm going to see a decrease in the force. That's an inverse relationship between those two things. And that's an important detail with this impulse and momentum change theorem. All right, so I want you guys to practice this again and fill out the rest of the table, looking at the idea of the impulse and momentum change being the same to figure out the velocity change, the force, or the other missing variables. All right, so filling out the rest of the table, here's what you'd get. So a couple relationships we will see here is obviously that you look at the second row, which I did. If you compare here, I just changed the mass. So here the mass got bigger. So notice if the mass gets bigger, it's going to give me more momentum. And then obviously the more momentum is going to require more force to stop that thing. Here the mass decreased. Notice that as the mass decreases, the velocity increases. So another relationship to understand is that if I increase the mass, that increases the speed. So again, that's an inverse relationship. So we see that same inverse relationship here as we see here with mass and speed. So there's a lot going on with this impulse and momentum change, but again, all this is just a deeper analysis of Newton's second law and how mass and speed and force and time are all related. All those variables are connected in terms of an object's momentum. Okay, here's just a couple quick examples, problem solving on using momentum and impulse. So we have Jennifer, who has a mass of 50 kilograms, is riding in a car at 35 meters per second. So again, that's her speed. She suddenly slams on the brakes to avoid hitting a deer crossing the road. She strikes the airbags, which are deployed, and her body comes to a stop in 0.5 seconds. So that's the time. And I want to know what is the force that's acting on here. So what we're going to do is we're going to use the impulse and change in momentum theorem. Okay, so F delta T equals M delta V. So I know that the force here is what I'm solving for. Delta T, which is given to you as 0.5 seconds, and just forget about some of the zeros. I know the mass of Jennifer is 50 kilograms, and I know her speed is 35. So again, the idea is that the momentum and impulse have to be, the momentum change, and the impulse have to be the same. So by multiplying these two, I'm going to get 1750, so 1,750 units of change in momentum. And that's going to equal to the impulse, which is going to be a force times that time. So essentially, I just want to know what force times a half would give me 1750. And that would give you an overall force equal to 3,500 newtons. So it would take a lot of force to bring Jennifer to a complete stop when she sees that deer. So now in example B, it says, what if she was not wearing her seatbelt and the airbag was deployed? And then it says the windshield and her airbag was not deployed, and instead of the airbag, it was her hitting the windshield. So when she hits the windshield, what happens is that the time is going to change. And the reason why the time is going to change is because there's not that much of a cushion. So if I did the same thing here, I did that impulse momentum change theorem, and now I know that the time is changed, 0.002, her mass doesn't change. She's still 50, and if she's riding in a car going at 35 meters per second, if she hits the airbag, she's going to come to a stop. If she hits the windshield, she's going to come to a stop. So her change in speed is still going to be 35 meters per second. So it doesn't matter if the time is different. What the time is going to affect is the force. If I were to actually solve for the force here, instead of 3,500 like I got in the last problem, what I would get is 875,000 newtons of force. Okay, so key thing here, folks, physics is going to teach you guys to wear your seatbelt because a seatbelt is going to just simply increase the time, well, this is again if you're using an airbag, but it's going to increase the time of contact, which is going to minimize the force you're going to have to experience. But again, this is just using that relationship of the impulse and momentum change theorem. All right, last example here. I know we're rambling with just a lot of terms to get through. So here, let's say we have a hockey player applies this force of 80 newtons to a 0.25 kilogram hockey puck. Over that time, what speed does the hockey puck gain? So obviously we have the force, we have the mass, and we have the time. Our goal is to solve for speed. So we're going to use the impulse, force times that interval of time, equals the momentum change, so mass times the change in speed. We know the force is 80. It's going to be applied over 0.1 seconds. It's going to be applied to a 0.25 kilogram hockey puck, and obviously that hockey puck is going to change its speed. It's going to get faster in this case, so we want to know what's that change in speed. So solving here, we're going to get a change in speed of overall 32 meters per second. So again, if it was at rest, it would go up to that speed of 32 meters per second. If maybe it was moving before, the overall change would be 32, which we could then use to determine what the speed would be at the end. So again, this is looking at the idea of impulse and momentum, momentum being a measurement of the motion of an object, impulse being the change in momentum, and then understanding the impulse momentum change theorem, where whatever impulse is acting on an object, that is going to cause the momentum to change, and that those two values are always going to be equal. So if you have any questions, make sure you jot those things down. I know this was a lot, so we'll talk about things in class, but good luck. We'll see you next time.